Welcome again. Today we will discuss organic reagents based on zinc and mercury. So as you can see, zinc and mercury are in the same group, but they are in the different row. This is 4th row and this is 6th. So we will discuss first the zinc. Organic zinc compounds, we will discuss preparation of organic zinc halides, applications of organic zinc halides, achiral reactions, enantioselective 1,2 addition, diastereoselective addition, then enantioselective 1,4 addition we will discuss. Also we discuss preparation of dialkyl zinc and its reactions, organozincates preparation and reactions, Reformatsky reaction, then Simon-Smith reaction, zinc reagents in cyclopropanation. This is an important reaction for cyclopropanation. Then Barbier reaction we will discuss, and Fukuyama coupling. This is ketone synthesis. So first we will discuss the basics about organic zinc reagents. Organic zinc compounds are among the first organometallic compounds made. They are less reactive than many other analogous organometallic reagents such as Grignard and organolithium reagents. This is an important thing. In contrast to the polar nature of CLi and CMgX bond, the CZN bond is highly covalent and hence less reactive, allowing the preparation of functionalized derivatives. So this is an important because the CZ bond is covalent, so you can incorporate functional groups. In 1848, Edward Frankland prepared the first organozinc compound diethyl zinc by heating ethyl iodide in the presence of zinc metal. This reaction produced a volatile colorless liquid that spontaneously combusted upon contacted with air. So they are pyrophoric in nature. Organozinc compounds are generally prepared using air-free techniques. They are also unstable toward protic solvents. For many purposes, they are prepared in situ, not isolated, but many have been isolated as pure substances and thoroughly characterized. So polar protic solvent is not good. Organozincs can be categorized according to the number of carbon substituents that are bound to the metal. The three main classes of organozincs are organozinc halides RZNX, that we will discuss, diorganozincs RZNR, that also we will discuss, and lithium zincates or magnesium zincates M plus R3Z minus with M is equal to lithium or magnesium. So first we will discuss preparation of organozinc halides. And primary and secondary alkali zinc iodides are best prepared by direct insertion of zinc metal, zinc dust activated by 1,2-dibomoethane or chlorotrimethylsilane into alkyl iodides, or by treating alkyl iodides with Rieke zinc. So this Rieke zinc we will discuss. The zinc insertion can tolerate a lot of functional groups, allowing preparation of polyfunctional organozinc reagents. This is important about zinc. And Rieke metals are highly reactive because they have high surface areas and lack passivating surface oxides. And this Rieke metal can be prepared. So the method usually involves reduction of a THF suspension of an anhydrous zinc chloride with an alkali metal. Typical alkali metals used in these methods are potassium, sodium and lithium. This way Rieke metal is generated. So you put zinc chloride, then lithium naphthalide, you get the Rieke zinc, and then you can put functional group containing Rx or simple Rx, then you can get functional group containing RZNX. That is the difference with Grignard. The functional group you can incorporate into RZNX. So R is equal to alkyl, aryl, benzyl, allyl. X can be bromine, iodine, functional group CO2 are enolate, cyanide, halide, etc. Even carbonyl also ketone. Reaction of functionalized substituted RZNI, this we will discuss. Or application of functionally substituted organozincs allows for construction of CC bonds while circumventing tedious protection deprotection strategies. Like here, you see this there is a triple bond and this primary iodide with zinc dust THF, you get this alkyl zinc iodide, And now 3-hydrocyclohexanone with copper cyanide, lithium chloride, then this coupling reactions happen. So, this is cross coupling reactions, and likely the oxidative additions is happening with copper, and then you get this product in 88% yield. So, this is the newly bond formed. Tosyl cyanide reacts with alkynyl or aryl zinc reagents to provide alpha beta unsaturated alkynyl or aromatic nitriles respectively. Like here, a chloro is there and vinyl iodide is there. First metal halogen exchange with n-butyl lithium, you get the vinyl lithium, and then treatment with zinc iodide, you get this vinyl zinc iodide. So, this is very important. Zinc iodide does not insert here, it insert here vinyl, because already the lithium is there. So, it is a nucleophilic reaction here is happening. And now, the tosyl cyanide, if you put then this, because this is a nucleophilic species, this is nucleophile, and tosyl cyanide is this CN. So, this is electrophilic species, electrophile. So, you get this product in 72% yield. Also, if a alpha beta unsaturated ketone is present and iodide, here you can put directly leakage zinc, and this does not add here. So, it inserts into this iodide, you get this alkyl zinc iodide and 60 degrees centigrade, and then in acid treatment you get the cyclization. So, this is the intramolecular cyclization is happening, intramolecular Michael reaction. Then you get this cyclopentane derivative. Now, we will see some enantioselective version, enantioselective 1-2 addition. Here you can add trimethyl aluminum promoted by addition of aryl zinc bromides and iodides to aromatic aldehydes. pH ZnBr was first converted to pH ZnMe by stoichiometric amount of trimethyl aluminum. Now, in situ form pH ZnMe was then treated with 4-chlorobenzaldehyde in the presence of catalytic amount of chiral beta amino alcohols. So, here first this exchange happens, pH ZnMe is formed, and this is the byproduct Me2LAX. Now, in situ if you prepare this with trimethyl aluminum pH ZnX with 4-chlorobenzaldehyde, if you react in THF toluene solvent room temperature 16 hours, you get this product, the pH group as to the 4-chlorobenzaldehyde with 63% yield, and with this amino alcohol. So, this is chiral amino alcohol, you get 83% EE. So, what could be the transition state? As you can see here, this complex is forms, the zinc coordinates with n-butyl, this is the tertiary amine and the oxygen, and now pH is coordinated of course with the zinc, and this is the pH ZnX, and also dimethyl aluminum which is byproduct, that also coordinates here. And now, this orients like this, aryl group will be this side, because if the aryl group this side, then there will be steric interaction with X. So, aryl group this side, and now phenyl comes from the top phase. So, this is C phase attack. The addition of pH group takes place from the C phase, and you get this stereochemistry. This was published in ChemCom 2007. Now, diastereoselective additions to immunoesters is also possible. Like here you can see this is immunoester, and this imine is chiral. Here this is the chiral auxiliary, and now diastereoselective addition can take place of nucleophile here. So, with zinc bromide ether and RZnBr 0 degree centigrade to room temperature, after ammonium chloride treatment you get this compound. So, the addition takes place from this way down phase. So, you get this product up to 68% yield and 92% DE, diastomeric excess. So, very good diastomeric excess up to 92%, and different groups like R is equal to tertiary butyl, you can add secondary butyl, cyclohexyl, benzyl, etc. So, what could be the mechanism of this reaction, and the stereochemical outcome of the reaction was explained by the proposed chelate models A and B. Both the models lead to R product. So, this is the chelate A and this is chelate B. So, there is slight difference. In chelate B, you can see the R, Z and X also is coordinate to the chiral auxiliary. So, here the chelate, here the R, Z and Br is externally coming. So, in chelate A, Z and Br2 coordinates to imine nitrogen and 2 oxygen atoms. So, Z and Br2 has been added previously, and it is coordinated to imine nitrogen as well as the 2 oxygen atoms. So, this makes a tight geometry, and now this rigid 5-member rings is formed, and the zinc reagent attacks from the least hinder rephase. So, that is why rephase attack is taking place, that is the down phase. So, down phase attack. In chelate B, zinc reagent may coordinate with the oxygen atom of the methoxy group, leading to preferential attack from rephase. So, here the R, Z and X is coordinated with this methoxy group, and this R now is taking place from the same the down phase. So, it is also down phase attack is happening. So, either by chelate A or chelate B you can get the same product. So, very diastereoselective addition is taking place. Now, enantioselective version is possible also with chiral catalyst. So, rhodium catalyzed enantioselective 1,4 addition of aryl zinc chlorides to protected 2,3-dihydro-4 pyridone to prepare synthetically useful 2-aryl 4-piperidone. So, this is the substrate, you can see this is the substrate 4-pyridone 2,3-dihydro of course, and here the nucleophile will add here. So, 1,4 addition will take place. Aryl zinc chloride is the reactant and RHCl R binap 2. So, this is the catalyst, chiral catalyst, and THF 20 degree centigrade you get this product, and you can get up to 95% yield, AR is equal to pH, and greater than 99.5% E. So, excellent enantioselectivity, excellent enantioselectivity with this binap ligand. So, rhodium R binap ligand you can get up to 99.5% E. This was published in JACS 2004. Now, we will discuss dialkyl zinc. So, unfunctionalized dialkyl zinc are obtained by transmetallation of zinc halides such as zinc chloride with organolithium or Gigner reagents. Iodide zinc exchange reactions catalyzed by copper iodide provides a practical way for preparing functionalized dialkyl zincs. So, this is the normal preparation. If you put 2 equivalent of isobutyl magnesium bromide, 1 equivalent zinc chloride, then 2 isobutyl goes to the zinc now. So, di-isobutyl zinc is formed, and this is the byproduct 2-MgClBr. Also, functional group containing RCH2I can be reacted with diethyl zinc with copper iodide catalyst. Neat, you can get this functional group RCH2 to zinc. So, dialkyl zinc, dialkyl zinc. Now, we will discuss reactions of diethyl zinc first. So, stereoselective additions reactions of diethyl zinc to aldehydes. So, here benzaldehyde is there, this is diethyl zinc, and with 2 mole% quinine toluene in 20 degrees centigrade 24 hours, and after acid workup you get this chiral alcohol, chiral secondary alcohol is formed, and this is the rotation. So, 68% E is obtained. So, what could be the mechanism? So, this is quinine, as you can see this is the alcohol of the quinine and this is the amine part. So, here so the benzaldehyde is coordinated with the OH. So, this is the acid. So, this is genyl acid, genyl acid. So, this is activating aldehyde. Now, your diethyl zinc is coordinated with nitrogen. So, both aldehyde and zinc are coordinated to the catalyst. So, it is now tight geometry, and that is why you can get enantiomeric excess. So, the ethyl group, this is coming from diethyl zinc from. So, nucleophilic addition of ethyl group is happening here, and you can get the secondary alcohol. This was published in JOC 1987. Now, we will discuss dimethyl zinc initiated radical reaction. They also can do radical reactions. There are a lot of radical reactions as you can see. So, what happens, a radical is generated, then it adds to defined electrophile. Like here, the radical will generate from R2 and it can add to the imine. So, this is imine. So, you can get a amine. Here also, this radical will form from here, from this acetal, and it can add to the chiral imine, and then this product can be formed up to 83%. Here also you can see, and tetrahydrofuran, the radical will form here. So, here the radical is formed, and then you can get this product. Also you can add this one, this tetrahydrofuran here missing here, tetrahydrofuran should be there, and you can add this dienamine, then you can get this product. Dr is 7:30. Then this one also is possible, the cyclopentane and the imine, then you can get this product. Also with this ester, iodoester, so you can get radical here, this can add to the imine, you can get this product. Also tetrahydrofuran and the amine, you can get this product. So, the one tetrahydrofuran is opening to give this component. Also this acetal and the alpha beta unsaturated ester, you can do the conjugate addition, you can get this product. So, various reactions can be done, various radical reaction by dimethyl zinc AR, and there is a review accounts of chemical research 2009. So, this is an example like this tosylamine. So, this is tosylamine reacting with dimethyl zinc 3 equivalent in THF solvent, you can get this. So, a radical is forming which is attacking the imine. So, you can get the Dr of 3:2 because 2 chiral centers are there. So, you get diastereomeric excesses. So, what could be the mechanism of this reaction? So, the mechanism that the formation of the adduct could be explained by a plausible mechanism which commences with the generation of methyl radical by the action of oxygen on dimethyl zinc. So, this is fast forming. So, dimethyl zinc plus oxidate, then you can get MEZNO dot and methyl dot. So, that methyl dot is reacting with tetrahydrofuran. So, tetrahydrofuran, then this radical is forming and CH4 will generate of course. So, resulting methyl radical then abstract an R hydrogen of THF to produce tetrahydrofuran 2-oil radical 12. Now, 12 can add to the imine. So, now if there is a imine, then this tetrahydrofuran radical will add to the imine and you generate the 13. So, which adds imine 1 to give a aminyl radical 13. Now, subsequent reduction of dimethyl zinc with 13 generates a methyl radical as the reaction carrier. So, when dimethyl zinc is added to here, then you get ZnMe and methyl dot is generated and zinc amide is formed. So, this is the amide which upon workup affords the product. So, this after workup you get this product NHR1. So, this is very important. The radical is from methyl dot radical and that is abstracting the R hydrogen from tetrahydrofuran. You get this radical and it is adding to the iminium ion or other electrophile and various reactions are possible. Now, we will discuss organozincates. So, organometallic reagent having Lewis acidic metal center possess ability to react with anionic fragment. Due to the presence of vacant orbitals on the metal center, these reagents when reacted with Lewis base form a new organometallic species which is termed as an 8 complex. So, the outer shell of zinc atom in dialkyl zinc like Me2Zn is filled with 14 electrons and there are 2 empty orbitals which can occupy 2 pairs of electrons. So, it can take more electrons Therefore, it can react with one or two Lewis basic reagent, as for example methyl lithium, which results in the formation of organozincates Me3Zn Li or Me3Zn Li2 respectively. So, dimethyl zinc again can react with methyl lithium, and then you can get this trimethyl zinc lithium. Organozincates are further classified into two classes: triorganozincates R3ZnM and tetraorganozincates R4ZnM2. And triorganozincates are generally prepared by the reaction of zinc halide with 3 equivalents of alkyl lithium or Gigner reagent, or from stoichiometric reaction of organolithium or Gigner reagent with diorganozincs. So, directly from zinc halide you can prepare zinc halide, then 3 Rm you have to put 3 Rm. So, there is 3 R3 will come here, then R3ZnM will form here. Alternatively, with dialkyl zinc react with 1 equivalent of Rm, then you can get R3ZnM. So, M is equal to lithium or MgX. So, these 8 complexes are very useful nucleophile that we will see, and it can be used defined additions reactions also. Triorganozincates have been used in many organic reactions such as 1,2 addition to carbonyl compounds, 1,4 conjugate addition to alpha beta unsaturated carbonyl compounds, addition to imines, metallation of aromatic halides, epoxide opening, and palladium catalyzed cross coupling reaction. So, many reactions can be carried out. As you can see here, this is the trialkyl zincate. So, trialkyl zincate. Now, when it adds to cyclohexanone, you get the 1,4 addition product. With imine, you get the amine addition to imine. Now, aryl iodide you can get R2Zn Rmn. So, metallation is possible. Epoxide opening is possible. Epoxide opening you can get product like this, alcohol product. Then cross coupling reaction with aryl iodide, palladium 2, and then you get this cross coupling product. And with ketone it can give the 1,2 addition product. So, this is the product. So, this is a very useful reagent, and the liquorophile it can add to various electrophiles like 1,2 addition, 1,4 additions, metallation and cross coupling, etc. Now, we will discuss Reformatsky reaction. This is very important reaction. The Reformatsky reaction, sometimes spelled Reformatsky reaction, is an organic reaction which condenses aldehydes or ketones with alpha haloesters using a metallic zinc to form beta hydroxy esters. The organozinc reagent, also called a Reformatsky enolate, is prepared by treating an alpha haloester with zinc dust. Reformatsky enolates are less reactive than lithium enolates or Gigner reagents, and hence nucleophilic addition to the ester group occurs slowly. So, this is very important, and ester group will be incorporated in the Reformatsky reagent, but the self condensation will not happen. So, that will happen very slowly. So, that is why you can use this reagent. The reaction was discovered by Sergei Nikolaevich Reformatsky in 1887. So, this is the reaction. You have to use the alpha bromo ester and a ketone or aldehyde, then you put the zinc, then of course, this Reformatsky reagent will happen, zinc will insert in this bond, severe bond, and after that nucleophilic you get this addition. So, then the zinc will coordinate with the oxygen, because this will be alkoxide, it will coordinate with this, and this bond is forming. After acidic workup you get this compound, this is beta hydroxy ester. So, these are very important compound. Beta hydroxy ester, because simply ketone addition with this Reformatsky reagent, that is the alpha haloester, and with zinc, then you get this intermediate. After aqueous workup you get this product. So, we will see first the mechanism. So, zinc metal is inserted into the carbon halogen bond of the alpha haloester by oxidative addition 1. So, this happens first, the oxidative addition. This compound dimerizes and rearranges to form 2 zinc enolates. So, 2 zinc enolates are forming here, because you can see there is a ester motif. So, of course, the enolate possibility will be there. the oxygen of an aldehyde or ketone coordinates to the zinc to form 6-member chair-like transition state 3. So, it is the enolate. So, this is very important. The zinc enolate is forming actually. Zinc enolate is forming. So, this is the zinc enolate formation you can see here. Now, zinc enolate is reacting with the carbonyl compound and a 6-membered transition state. So, this is the 6-membered transition state. This we have seen earlier also. And here if you see this R2 and this OZNX are trans. So, here also R2 and OZNX they are trans. So, you have to maintain in the chair also. And now, this carbonyl also will be coordinated with the zinc and it can take orientation like this. Then a rearrangement occurs in which zinc switches to the aldehyde or ketone, oxygen and carbon-carbon bond is formed. So, after carbon-carbon bond forms you get this. So, this is the newly bond form is forming and here this a carbonyl group will form here and this will be the OZNX. Acid workup 5,6 removes zinc. So, this will form. Now, acid workup removes zinc to yield zinc to salts and beta hydroxy esters. So, acid workup this will be byproduct and this is the beta hydroxy ester. Because acid workup will remove the zinc. X minus will react here and then you get the free alcohol. So, this is the reaction, that is the zinc enolate and a 6-membered chair-like transition state will form. These are the main things and after that you can get the after acidic workup beta hydroxy esters. So, we will see now defined application of this reaction, because the beta hydroxy esters you can of course convert to alpha beta unsaturated esters also. Acid catalyzed dehydration gives alpha beta and beta gamma unsaturated esters mixture. If you see this substrate cyclohexanone and BrCH2 CO2 alpha momo esters with zinc benzene, you can get this product, that is the Reformatsky reaction beta hydroxy ester. Now, on this if you put acid, what happen? You can get two products. So, CO2 plus the internal double bond is also possible. CO2. So, that is why the acid catalyzed dehydration gives alpha beta and beta gamma. So, this is alpha beta, this is beta gamma. However, conversion of the initially formed beta hydroxy esters to their corresponding acetates by treatment with acid chloride followed by base catalyzed dehydration with sodium ethoxide produces conjugate ester in high purity. So, now if you do not do the acid treatment, alternatively you can put with acid chloride and dimapyridine, then you can protect this hydroxy as the acetate. So, acetate formation happens and now if you put sodium ethoxide as a base in ethanol solvent, the beta elimination greater than 90% and selectively you get this. So, selectively alpha beta unsaturated ester is forming, because it is now base mediated elimination. So, this proton must be more acidic. So, the elimination will happen from there, you can get this alpha beta unsaturated ester in greater than 99:1 ratio. So, this is the beta gamma. So, here only single product is forming. So, this is very important reaction. If you treat with acid chloride, then you get the acetate and after base treatment you can get the alpha beta unsaturated ester. Now, double Reformatsky reaction also is possible and here divergent synthesis of delta hydroxy beta keto esters. Simple this zinc ester they do not dimerize, see this is 1%, because already we told that this zincate they are much less reactive. So, this says they are less reactive and that is why it does not react with esters. But some cases like this one, this is the special ketone, a pyridine motif is there and a phenyl group. Now, you put this reagent, Reformatsky reagent 3.5 equivalent THA minus 20 degree centigrade 4 hours, you get this product, this is the normal product, beta hydroxy ester forms 97% and 3% this one, this is the double Reformatsky. So, if you run this compound again, because excess is there, the second Reformatsky reaction will happen. So, this step second Reformatsky reaction is possible. This is unusual. We will see the mechanism. The pyridine group is important for this reaction. Now, if you start for room temperature 4 hours, then 2A become 3A and 98% 3A is formed. So, 98% and 2% only remains as 2A. So, what is the mechanism here? Now, the key to accelerate the double Reformatsky reaction is considered to be a complex induced proximity effect of the in situ generated zinc alkoxide coordinated with the pyridyl group. So, this pyridine motif is important of the substrate or bidentate amines. So, this is the mechanism. As you can see, this is 2A, this is the dimeric structure, dimeric, and this is the Reformatsky reagent here also. So, what happens if you see the structure? Now, this A star is activated by zinc bromide, which is coordinated with the pyridine. So, this is important. This is again activated, so that nucleophilic addition will happen again. So, how it is activated? No, this way it is activated. This nitrogen and this oxygen coordinated with the zinc, and that activated zinc coordinated with the A star carbonyl. Similarly, here also this is the dimeric, here also the A star carbonyl is coordinated with this zinc, which is activated with this hydroxy and pyridine motif. So, this is very important. The pyridine group, if you have a pyridine group, then the double Reformatsky reaction can work. This is the potential transition state of the reaction of 2A to 3A, and this was published in Journal of Organic Chemistry 2013. Now, if you add bases externally, like this benzophenone is there. So, this is benzophenone, and with this Reformatsky reagent 5 equivalent, if you add different bases. So, these are the additives, different of course bases are there, and THF room temperature 3 days. So, this is the double Reformatsky product as you have seen. So, here you can see if there is no additive also you can get 48% yield, but if you add bases like pyridine, it is giving 78, pyridine 4 equivalent 75, 2,2 bipyridine is giving 91, and the base is TMEDA, which can give 95% yield. So, what is happening here? Because the amine is coordinated with the zinc, free zinc, and that is activating the A star. So, that is why the external base, so this is the external base, can give double Reformatsky product. So, this is very important. Efficient synthesis of alpha amino acid by homologation of beta amino acids involving the Reformatsky reaction and manic iminium electrophile. So, this is another application of Reformatsky reaction. So, this is alpha amino acid. So, this is chiral alpha amino acid. Now, if you do diazotization, so if you put NaNO2, NaBr and H2SO4, then you can get this bromine here. So, first the diazotization will take place, then NaBr will react, you can get this bromine here, and also the acid can be converted to the A star. So, acid if you put H2SO4 and R-OH, that is the alcohol. So, acid catalyzed A star synthesis can be formed to get the A star. Now, this you can get the Reformatsky reagent after reacting with zinc, and that reagent you can react with this iminium ion. So, this is the iminium ion, double bond N benzyl 2 CH2, also CF3CO2 minus is there. Now, your nucleophile will attack here and you get this. So, the chiral center will not be disturbed here. So, we will like this. So, this is the newly bond formed, and so this is beta amino A star, and after that of course after hydrolysis you can get the beta 2 amino acid. So, this is very important, you can convert alpha amino acid to beta amino acid, and this was published in Journal of Organic Chemistry 2006. Also total synthesis, it has been applied, total synthesis such as the synthesis of C16, C18, bis, AP, cytochalacin D. So suppose this was the intermediate, and you can see here, of course electrophile is there, and also this alkyl chloride is there. Now if you put zinc, that was the interesting thing about zinc, that it can add selectively to this bond. So you have to activate the zinc, that is the activated zinc with sodium naphthalene, zinc chloride. Then it adds to here, and after that the addition takes place, and after acid treatment you get this alpha beta unsaturated ketone. So what happens if you see the mechanism? So zinc chloride or CHO here, of course a Me group is there. So this will add, so you get OH. Now if you put acid, what happens? Acid, because this will become ketone, of course, in acid, methyl OHR. So this will form, and this after elimination of water, it will give the alpha beta unsaturated ketone. So here methyl group will be there. So that's what here is happening. You see, this is the double bond and alpha beta unsaturated ketone. Now this compound can be converted to this. So here you have to convert this to hydroxy. Here a double bond has to incorporate, and then a quaternary center. So this is the C16, C18, bis, AP, cytochalacin D. So that's why Reformatsky reaction is very important, and this was published in Journal of Organic Chemistry 2000. Now we will discuss another reaction, Simon-Smith reaction. This is cyclopropanation, zinc reagents in cyclopropanation. This is the most important reaction involving an organo-zinc reagent. The iodomethyl zinc iodide is usually prepared using zinc activated with copper. The iodomethyl zinc iodide reacts with an alkene to give a cyclopropane. The reaction is stereospecific with respect to the alkene. Mechanism is concerted. For example, if the alkyl groups of the alkene are cis, then they are also cis in the cyclopropane, and trans alkene gives trans cyclopropane. So this is the syn addition, and like cyclohexene, if you put with CH2I2 and zinc copper couple with ether 35 degrees centigrade, you get this product. So this is syn addition. And what happen if you put this CH2I2 zinc copper couple in ether 35 degrees centigrade? This is the active intermediate that is forming ICH2 zinc iodide, iodomethyl zinc iodide. So this is forming, and which is reacting with the double bond. So mechanism we will see. So first published in JACS 1958. Now mechanism, so a concerted reaction, both new CC are formed simultaneously. Best views as the nucleophilic C double bond C causing loss of the iodide leaving group, and the electrons from the nucleophilic CZ bond being used to form the other CC bond. So this CC bond is forming like this. This is the leaving group, and this is now nucleophile. So this bond is attacking to the double bond, so that you get this CH2 group, and ZnI2 will be byproduct. So this is concerted reaction. And butterfly like transition state also is possible. You can see here the CH2 group is adding to the double bond, the pi electron cloud are delocalized. Here 2 3-member rings are there. And now the characteristics we have already told: the stereospecificity, retention of the olefin geometry, tolerance of a variety of functional groups such as chloride, bromide, OH, OR, CO2R, carbonyl and cyanide. This is very important. So selectively only it reacts to the double bond, not to the carbonyl. The syn directing effect of hydroxyl and ether functions, this we will discuss. The directing effect, so this is directing effect. And chemoselectivity, zinc carbinoids are electrophilic and react chemoselectively with the more nucleophilic double bond in dienes and polyenes. So, if you have many double bonds, then the more nucleophilic double bond will react. So, now many zinc reagents for cyclopropanation have been developed, the alternatives like this is the Simmons and Smith, that is the iodomethyl zinc iodide, then here the Denmark developed, then Furukawa developed with ethyl zinc, actually the ethyl group, this is CH2I group. So, these are general applicable, but we will see, and C group develop a trifluoroketone is there, and this is highly reactive carbinoid for unreactive alkane. So, this is highly reactive, and Charette developed with this phosphate, and this is highly stable. So, one is highly reactive, another is highly stable. When the phosphate is there, at that time it is become highly stable. So, this is the Furukawa reagent iodomethyl zinc derived from diethyl zinc and diiodomethane, or its modification using chloroiodomethane instead of diiodomethane allows more flexibility in the choice of solvent. The reagent is homogeneous and the cyclopropanation of olefins can be carried out in non-complexing solvents such as dichloromethane or 1,2-dichloroethane, which greatly increase the reactivity of zinc carbinoid. So, this is very important, this Furukawa reagent. The other non-complexing solvent like dichloromethane, 1,2-dichloroethane can be used. So, this is an example, this is Furukawa reagent. With Furukawa reagent, this reaction cyclohexene, diethyl zinc, CH2I2, benzene is a solvent, 60 degree centigrade, you get this product 79% yield. Also here transalkene is there, PHCH3 with same reagent diethyl zinc, but here ClCH2I and 1,2-dichloroethane solvent, you get this product. So, this is the trans product, you getting 92% yield. So, that is the importance of Furukawa reagent, you can use different solvents. Now, we will discuss directed cyclopropanation is possible in the presence of directing groups. Stereochemistry is due to ankymeric acceleration. The stereoelectric control exhibited by proximal OH-OR groups which favor cyclopropanation to occur from the same phase of the double bond as the oxy substituents. An order of decreasing directing effects OH greater than OR greater than carbonyl. So, this is, you can see this is of course racemic allylic alcohol, allylic secondary alcohol. So, what happens, this alcohol of course this is a chiral center. So, in the product you see this cyclopropyl group is in the same side of the hydroxy. So, with CH2I2 zinc copper ether 35 degree centigrade you get 63% yield of this product. So, cyclopropyl in the same side with hydroxy like epoxidation. Not only hydroxide, the ether, so this is defined with epoxidation, here the ether also can direct. So, ether CH2I2 zinc copper you get the same product, the cyclopropyl group in the same side of the methoxy and you get 60% yield. So, what could be the mechanism? So, here you can see this half chair conformation. So, this is the half chair conformation, here the cyclohexene group, this is the double bond and OR in the top. Now, this OR will complex with the zinc. So, this is important, OR or OH is complex with zinc, IZNCH2I. So, that is the active reactant, where here this is the active reactant is coordinated, the coordination happens. So, the addition is taking place from the same side of OR. So, here from the top face, and so this is the product, you get the cyclopropanation from the same side of the OR group. So, because of this coordination you get this geometry. Now, we will see some more directed examples, like here this is an sugar motif and interestingly one OH is free. So, this is free OH, and you see this is ether, a double bond is present here, this is of course trans alkene. Now, with diethyl zinc CH2I2, that is the Furukawa condition toluene minus 35 to 0 degree, 98% yield, and DR 50 greater than 50:1. So this cyclopropionation happens. So same side of OH. So cyclopropionation happens same side of OH. Of course, this is a chiral auxiliary, so that has to be clipped. So if you put first triplet anhydride pyridine, you get this O triplet, and after that DMF water pyridine condition, you can get this product, alcohol product, cyclopropyl alcohol, and this ring contraction happens. So here ring contraction and aldehyde is formed. So this is the transition state. So here you can see this cyclopropionation happening is double bond. So here this CH2I group is present. Now zinc is coordinated with, of course, the hydroxy. This is the hydroxy group as well as this ether group. So double coordination is happening, and now the cyclopropyl group will come from the same phase of the OH group, and you get this geometry. This was published in JACS 1991. Not only this is also you can see beta amino alcohol. Chiral beta amino alcohol is the chiral auxiliary. So this is the double bond. Here also trans double bond is present. Of course, this is the chiral auxiliary. Amine hydroxy is present, and with diethyl zinc CH2I2 same condition. Dichloromethane 0 degree centigrade, you get 95% yield, and DR is equal to 98:2. So it is very important. Here also the top phase, cyclopropionation from top phase, that is from the hydroxy side. So the coordination is happening similar way, and you get this product. This was published in Organic Letters 2003. Now we will discuss asymmetric versions, reagent controlled, or catalyst controlled, that we will see. So homoallylic ethers can be cyclopropionated using a zinc phosphate prepared in situ from a chiral phosphoric acid. So if you have this homoallylic ether, O-benzyl ether, and B is this phosphoric acid with this substituent, AR is here, 3,3' substituent, and when it is treated with diethyl zinc CH2I2, then this zinc phosphate is formed. So this is in chiral environment, and this is used in 1.2 equivalent, and the product cyclopropionation happens in 85% yield with 93% enantiomeric excess. So this is very high E. And this group are required for this control of high enantiomeric induction. This work was published in JACS 2005, page number 12440. So this is reagent control, because one equivalent you need. And now we will see catalyst control. So chiral bisulfonamides have been used to direct asymmetric Simmons-Smith reaction of allylic alcohols. This is allylic alcohol, and with this bisulfonamide, this is C2 symmetric. This is 10 mole% only, then diethyl zinc, zinc iodide plus zinc CH2I whole 2 with dichloromethane solvent 0 degree centigrade, you get these cyclopropionation products in 92% yield with 89% E. So this is very important. Only 10 more% of this catalyst can give very high yield as well as very high EE. This work was published in Journal of Organic Chemistry 1997, page number 584. Now we will see another reaction. The Barbier reaction involves nucleophilic addition of a carbanion equivalent to a carbonyl. The conversion is similar to the Gigner reaction. The organozinc reagent is generated via an oxidative addition into the alkyl halide. The reaction produces a primary, secondary or tertiary alcohol via 1,2 addition. And the Barbier reaction is advantageous because it is one pot process. The organozinc reagent is generated in the presence of the carbonyl substrate. Organozinc reagents are also less water sensitive, thus this reaction can be conducted in water. So, this is very important, it can be conducted in water also. So, carbonyl compound R3ZNX, the 1,2 addition happens and after aqueous acid workup you get this alcohol. So, this R3 is coming from the zinc. The mechanism resembles the Giggner reaction in which the metal alkoxide can be generated by a radical stepwise pathway through single electron transfer or concerted reaction pathway via a cyclic transition state. So, this kind of possibility is there either by a radical pathway or by concerted reaction pathway. Now, we will see examples. So, this is propargyl bromide. So, with zinc THF, first this propargyl zinc bromide will form, that will add to the aldehyde and you get the secondary alcohol. Also, allyl bromide, if you put zinc, water. So, this is very important, water can be solvent, zinc, water, THF and benzaldehyde, you get this product. So, here the zinc is formed, so this is the newly bond formed. And propargyl bromide can also be reacted with this dienal. So, this is dienal with zinc THF, then the protection TBS chloride. So, alcohol is protected as TBS and the terminal CH, that is the alkyne CH, can be deprotonated with N-butyl lithium, then carbon dioxide treatment will give you a CO2H group, and this intermediate can be converted to this cycloproparadicol. So, this you can see this geometry. So, some functionalities are coming from this here, like this one most likely. Now, we will discuss Fukuyama coupling, that is the last reaction of zinc. So, Fukuyama coupling is a coupling reaction taking place between a thioester and an organozinc halide in the presence of a palladium catalyst. The reaction product is a ketone. This reaction was discovered by Tohru Fukuyama et al. In 1998. Advantages are high chemoselectivity, mild reaction condition and the use of less toxic reagents. So, this is an important thioester and zinc, alkyl or aryl zinc. With palladium catalyst, of course, you get the ketone. So, this is very important reaction and the mechanism like this, oxidative addition of the thioester is followed by transmetallation. Now, palladium 0 of course here, now thioester, the oxidative addition happening. So, oxidative addition, COS bond here, the palladium is inside, palladium 2 now. Now, the transmetallation will happen, transmetallation from the zinc compound. So, R dash will come to palladium and this will be byproduct ETSZNI. And now, this is the reductive elimination. Reductive elimination will happen. So, ketone will get and palladium will regenerate, leads to the coupled product. So, we will see some examples, like here a carboxylic acid, you have to first convert to acid chloride, then you treat with ethylamine ethane thiol, you get this thioester. So, this is thioester, and with palladium chloride PPH3 ETZNI, toluene room temperature, only 5 minutes you get this product ketone. So, this is very fast process, very fast, only 5 minutes you get this ketone product. Direct synthesis of unsymmetrical ketones. So, this is the thioesters R-ZnBr PD2DBA3 1 mole percent, PCY3 2 mole percent, zinc chloride 1 equivalent, THF 28 degree centigrade 12 hours you get this ketone. And here various zinc can be used. So, this is the thioester. So, this is the zincate part. Here also aliphatic, here also aliphatic, here cyclopentyl group, and here benzyl group. So, the yields are good here 92%, 93, 94, 88 and this one 58%. This was published in Tetrahedron 2014. Now, we will see example like here this is 1-methyl cyclohexene. If it reacts with mercury acetate, water, ethanol, then you can get this one regioselectively. So, alcohol is more substituted, and after that sodium borohydride treatment with water diethyl ether with a base, you can get the removal of the mercury and you can get this alcohol, free alcohol. So, this is oxymercuration and this is demercuration. So, we will see now details mechanism. So, step 1, the C11C pi electrons act as nucleophile with the electrophile mercury and loss of an acetate ion as a leaving group, forming the cyclic mercurinium ion. So, it is happening like this. So, this is the cyclic mercurinium ion, cyclic mercurinium ion. Now, water attacks as a nucleophile and carbon substitute with mercury, resulting in cleavage of the CH bond. So, this will form, and now acetate ion function as a base, deprotonating the oxonium ion to give the alcohol. This completes the oxymercuration part of the reaction. So, now this you get, and the alcohol the more substituted carbon atom because of the Markovnikov addition. Now, the demercuration reaction has eluded full understanding the mechanism of the reductive replacement of mercury by hydrogen. Demercuration most likely involves a free radical intermediate produced by decomposition of alkyl mercury intermediate. So, most likely hydride will react with this mercury and this HGH bond will form, and after that homolytic cleavage will happen and this radical will form. This is the radical and Hg dot H of course, and now again it will react this radical with H and this will go to mercury 0. So, you can get the alcohol. So, this is the demercuration is happening. Support in favor of the free radical mechanism comes from the observation that oxygen, an efficient radical scavenger, can divert the reaction, and this was published in JACS 1974. And the regioselectivity and stereospecificity of the oxymercuration reaction with substituted cyclohexenes, a bulky group like tertiary butyl locks the ring in a chair conformation and prevents ring flips. With 4 tertiary butyl cyclohexene, oxymercuration yields 2 products, where addition across the double bond is always anti, with slight preference toward acetoxy mercury group trans to tertiary butyl group, resulting in the slightly more cis product. So, here you can see 4 tertiary butyl cyclohexene oxymercuration reaction gives 2 products. This is almost equal amount because after sodium borohydride THF sodium hydroxide treatment you get this. So, mercury addition to the downside is little bit major, it is forming 54% and this is 46%, this one. Now, with 1-methyl 4-tertiary butyl cyclohexane, oxymercuration is only one product, still anti-addition across the double bond where water only attacks from the more substituted carbon. And the reason for anti-addition across the double bond is to maximize orbital overlap of the lone pair of water and the empty orbital of the mercurinium ion on the opposite side of the acetoxy mercury group. And regioselectivity observed to favor water attacking the more substituted carbon, but water does not add syn across the double bond, which implies that the transition state favors water adding from the opposite side of the acetomercury group. So, this is the 1-methyl 4-tert-butyl cyclohexene, and now if you do chair like after mercury acetate you get this product where this mercury acetate is opposite of the tertiary butyl, and of course water attacks from the opposite sides. OH is like this and methyl will be down, and with sodium borohydride treatment you get only this single product. So, only single product is forming. So, this is very important. Mercuric acetate will be transferred to the tertiary butyl. So, water will come from the opposite side antiphase. So, you get this product. Oxymercuration is not limited to alkene reacting with water. Using an alkyne instead of an alkene yields an enol which tautomerizes into a ketone. Using an alcohol instead of water yields an ether. In both cases Markovnikov's rule is observed. So, this is alkyne Hg2 plus, you get the enol tautomerization to ketone, and with an alkene that we told earlier that with alcohol you can get an ether. So, this is an ether is forming. And using a vinyl ether in the presence of an alcohol allows the transfer of the alkoxy group RO from the alcohol to the ether. An allylic alcohol and vinyl ether under the condition of oxymercuration reaction give RCH, CH, CH2O, CH, 11CH2, which is suitable for a Claisen rearrangement. So, this is the reaction RO vinyl ether. So, this is vinyl ether and with an alcohol R-OH. So, R- coming here and ROH is the byproduct. So, this is the exchange happening. We will see the mechanism. So, what could be the mechanism? Now, this vinyl ether first coordinates with the mercury to generate the oxonium ion, and to the oxonium ion the alcohol will add to generate this acetyl derivative, and after that deprotonation or HX plus transfer will happen. So, here the proton goes to this part now, and again another oxonium ion. So, again oxonium ion will form, oxonium ion, and ROH is the byproduct, and after Hg removal, so after removal you get this vinyl ether Hg2 plus and ROH. So, this is the vinyl ether. So, this is the mechanism of the vinyl ether, the transfer of the alkoxy group. So, it is the alkoxy group R-O, that is, because here you can see this is the red oxygen, earlier oxygen was black, this is red oxygen. So, the R-O alkoxy group is transferring. So, today in the class first we have discussed preparation of organozinc halides, then we have discussed the application of organozinc halides. First the achiral reaction we have discussed, then enantioselective 1,2 addition, diastereoselective addition, then enantioselective 1,4 addition reaction with rhodium catalyst also we have discussed. Then we have discussed preparation of dialkyl zinc and its reaction. It undergoes many radical reaction because dimethyl zinc it generates the methyl dot radical and which generates the tetrahydrofuran suppose, then the tetrahydrofuran radical will form which can add to defined electrophiles. Then organozincates, their preparation we have discussed, and reactions it can add defined addition products 1,2 addition, 1,4 additions, and also palladium catalyzed coupling reactions it can do. Then we have discussed the Reformatsky reaction. It is an important method for generation of beta hydroxy esters. Also we have seen the double Reformatsky reaction. If you have a pyridine in the ketone, then the double Reformatsky reaction can happen because the pyridine coordinates with the zinc. Siemens-Smith reaction, this is very important reaction for cyclopropanation, and also you have seen the more reactive double bond will react and will be a directing group also. If you have a hydroxy group, also an ether group that can coordinate with the zinc, and the cyclopropanation will happen from the same phase. Then we have discussed the Barbier reaction. This is like Grignard addition, so it is similar, but here you can use the water as the solvent. And lastly, we have seen the Fukuyama coupling, which is a ketone formation from thioester and alkyl zinc compound with palladium catalyst. And in the mercury, we have discussed oxymercuration, demercuration. This is the Markovnikov addition to generate alcohol from olefin, and you can get the more substituted alcohol here. Thank you.